Right, this is your May 2015, and as we mentioned, you can actually see that as we talk about, you can see the requirement given to you, right? State space, state the Laplace transform of a delay of t seconds, and hence determine the magnitude and phase of the frequency response of a delay of t seconds. So again, as I mentioned, you will see this thing popping up over and over again. So it's something that you need to basically familiarize yourself with, right? So no longer you just know how to do the calculation, you also must remember how to state the definition in terms of, so far what we have seen your root locus. I think root locus you have not seen. We have seen typically your delay. So root locus is also something that you need to prepare yourself. Root locus, your polar locus, frequency domain analysis, gain margin, phase margin, root per base. Okay, root locus, polar locus, frequency response, gain margin, phase margin, stability requirement. Okay, so those are the things that they will just ask you. Though it's only 2-3 points, but sometimes it matters between the A1 and the A2. Alright? So in this problem again, I guess the first part I'll leave it to you all. It's straightforward. You can actually extract it from your notes. The part B, you have a simplified model of a helicopter. So, like I mentioned, right? Simplified model of helicopter. So this is basically a lower order approximation. Okay, this lower order approximation helicopter frequency response from engine throttle position to vertical. So you can imagine this is only from engine throttle position to vertical position. So you also can have engine throttle position to forward. You have engine throttle position to side. So you can imagine this is only linear axis. Each one of them is a third order. You multiply by 3, it's already a 9 order. Then you add in the rotational and so on and so forth. Okay, so this only in engine throttle position to vertical position of the helicopter can actually be modeled as such. Okay, so nevertheless, we know from here, they ask you to plot an accurate Nyquist plot for this system. You should use, so this one is actually kinder. 1 unit is equal to 5 cm. Calculate data points at a frequency 0, 2, 4, 8, 16, 32, and infinity and so on. So typically, whatever we discuss is still valid because we talk about 0, we talk about infinity. So that's why I told you, right, it cannot go wrong. So in this case here, this is a case where you have 3 poles and 1 0. So you have corner frequency, that's what we mentioned. You need to identify your corner frequencies, alright? So in this case here, your corner frequency, you have what? You have omega, you have an integrator. So then the first corner frequency is going to be 4, and then you have 8, and you have 16. Alright, but you have to bear in mind that you have an integrator. So the relative order for this system is going to be equal to 3 minus 1 is equal to 2. So straight away, we know when frequency is very small, when frequency approaches positive infinity, what will be your magnitude? So this one, as we discussed, because you have an integrator, anytime you have an integrator, magnitude will be infinity at low frequency. And because you have an integrator, your angle is going to be controlled by the number of integrator you have. In the system, in this case here, it's going to be minus 90 degrees. Alright? When frequency approaches infinity, what will be the magnitude? Because we mentioned before, when we talk about your transfer function, I mentioned to you, you still remember a strictly proper and a proper system. Can you still remember? Cannot. Hey, you are working on 2 GB of memory. I'm working on 64K. You know. When you have a strictly proper system, you have more poles than 0, right? N is greater than. Strictly proper is n greater than n because n is basically 0, order of 0. This is order of pole. Okay, so this is actually strictly proper. I thought triple E guys, this is a standard thing you all learn. When you have a strictly proper, you have what we call high frequency roll off. What do you mean by high frequency roll off? High frequency roll off meaning at high frequency, your magnitude becomes very small. Okay, so you have a high frequency roll off. If you have a proper system, that means your n is equal to m. Right? And we discussed it at the very beginning. We said, okay, when you have a proper system, n is equal to m. So, do you have high frequency roll off? No, you don't have a high frequency roll off, but your high frequency magnitude will approach a constant. Right? The high frequency magnitude will approach a constant value. Agree? Agree or not? Your high frequency magnitude will approach a constant because you have equal number of poles and zeros. Okay, so if you remember your straight line approximation, eventually at high frequency, when you pass all your corner frequency, the number of poles and the number of zeros, the slope basically balances it out. So when you approach high frequency, you are actually moving at 0 dB per decade. Right? 0 dB per decade instead of minus 20 dB or minus 40 dB per decade. So as a result, you taper off as a horizontal line, so you actually have a constant value. Okay, so that is your proper system. So in this case here, we have a strictly proper system because we have 3 poles and 1 zero, so magnitude will be equal to 0. And then your angle, because the relative order in this case here is 2, so this is minus 180 degrees. So these 2 points you don't have to calculate. Right? But the rest of the points, unfortunately, you need to calculate. Right? Because why? Because the problem basically will give you, so you need to basically work out the equation. So again, this is a challenging problem for you that you need to actually work it out. So this is 10 and then square root of 1 plus omega squared divided by 64, and then divided by, at the denominator, you have omega, you have the square root of 1 plus omega squared divided by 16 times your 1 plus omega squared divided by 169, right? Okay? Is it 169, 16 squared? Okay, no, wrong. No, what is that? 256. Is it 256? Yeah, 256 because it's 8-bit, right? 16 is a 4-bit, 4-bit, so 8-bit is 256. Yeah. Okay, alright, so this is the magnitude, and then of course, when you work out the phase angle, GJ omega, 0 minus pole, so you have arctangent of omega divided by 8, minus 90 degrees because it's a pole at the origin, constant minus 90 degrees, then you have minus arctangent of omega divided by 4, minus arctangent of omega divided by 16. Okay, so these are the two equations you need to try to work out the rest of the point at omega is equal to, so 0 we have worked it out, so we need omega is equal to 2, 4, 8, 16, and 32. Okay, so basically 4-bit, 5-bit, so you need to work out 1, 2, 3, 4, 5, 5 times 2, 10 points. Okay, so this is only the first part of it. When you work it out, so in a way, so what happened here is you need to try to go back and you try to plot it. Okay, when you try to plot it, you, okay, so I cannot write it this way, sorry, This one, because what you're plotting it is basically you're plotting it at the G plane. At the G plane. So this is actually real G, okay, GJ omega, real GJ omega, and this is actually imaginary of your GJ omega. Okay, so this is a G plane. So when you work it out, you can actually see that it depends on how we actually do it. So we know that the low frequency is going to be minus 90. So anyway, it will be coming from this point here. Okay, so if you are far down, so you actually see that this thing is actually coming in this way. Okay, because what happened here is when you are increasing, the first corner frequency is actually a pole. So it will be more than minus 90, but eventually it will actually increase because of the zero corner frequency. So when you hit the zero corner frequency, zero contribute positive phase. So you actually move away, and then eventually the last one is the last pole at 16 radians per second. But as what we know, at high frequency, so this is actually at high frequency. So this is actually at low frequency. So this point is actually high frequency. This point is actually zero positive. Because in your polar locus, you have actually two portions. So typically what we do is we plot zero positive to positive infinity. There is also a zero negative to negative infinity, that negative infinity to zero negative, that we didn't actually work it out. But it's just a mirror image. So typically if you do the bottom, you can actually flip it. Okay, you can actually flip it. So in a way, you can actually have this. To be basically symmetric about the whole thing. So if you try to plot it in a symmetrical sense, that's how it looks like. Okay? So this one will be omega approaches infinity. This one will be basically your omega is equal to zero negative. Okay, but the top part, don't have to worry. Do the bottom part will be good enough. Okay, so the next portion of it, they ask you to explain from your plot, explain why the gain margin of the system is infinite. Okay, why the gain margin of the system basically is infinite. So in a way, when you work it out, so how do you plan to explain the gain margin is infinite? Okay, so if you remember, that's a problem that if you were to plot this, unless you magnify it. So what does the gain margin depends on in the polar locus? The gain margin depends on the minus 180 degree crossing of your phase curve, right? You need to basically determine, because if you were to think of easier two diagram, your phase must cross minus 180 degree line. When you cross minus 180 degree line, basically it's like your polar locus crossing your negative real axis. Okay, so you must cross the negative real axis, because why? Because then you cross into a point where your angle can be less than minus 180 degree. So the important thing for gain margin, the determination of your gain margin is your polar locus must cross your negative real axis. And in this case here, you see that it actually does not cross your imaginary axis, because if we were to expand it or enlarge it for this, maybe this is what you will see. So this is your minus 180 degree. The thing basically comes this way. Not very nice. Okay, so if I have to enlarge it, basically if I see this, so if my polar locus is actually coming in this way, I can multiply by 1 million gain and all this and that. Are they going to encircle your minus 1 point? Because with this, what happens is if I change the gain, so what is the effect of changing the gain for this polar locus? So if you change the gain, is this going to be like this? Okay, you go and take a look at the textbook by Franklin and Powell. I think they will show you. So this is basically K increasing. Okay, when you increase the gain K, this is what happens. But where is your stability boundary? Your minus 1 point is here. So are you going to encircle your stability boundary? No. That's what we discussed before. If you're just basically making use of your gain, you will not be able to destabilize unless you add phase lag. Right? Into the system, you introduce a phase shifter or something like that. Into the system, you can actually destabilize the system. But based on what we do, a normal analysis, your gain margin, phase margin, you will not be able to destabilize the system. So in this case here, this is the case, how we actually explain why your gain margin of the system is actually infinite, because it does not actually intercept your negative real axis. Okay, because the root locus, your magnitude of your gain margin can be determined when the root locus actually crosses, your polar locus actually crosses your negative real axis. So as a result, in this case here, we don't have that, so we are very sure that the gain margin is going to be infinite. So now they ask you to find the frequency at which the magnitude of the system is equal to 1. Okay? Find the frequency at which magnitude is equal to 1. That means you come back to this point here. So what you need to do is you have a unit circle. Okay, so this is a point. So meaning you need to go back to this equation, magnitude is equal to 1. Okay, magnitude is equal to 1, and you try to work out the equation. And that is why I mentioned to you a lot of time, are they giving you? Let me see, I'm not too sure whether you are even. One of this, okay, find the frequency at which the magnitude of the system is equal to 1, and hence shows that the phase margin of the system is 49.05 degree. Am I looking at the correct question? Yeah, this is the correct question, right? Wow, how to do this if I don't get the equation? Because when I square it, it's going to be a problem, right? When I square it, wait, how come they were given this only? Because if you were to square this from this magnitude equation, it becomes 4 times, and then omega, so there's 6 times already. Okay, so this one, you can work on it. Let me go back and try to figure it out. How actually to make use of this? You must make use of this, because this one is not going to be given to you without any. I think there might be some error in this. Anyone work it out? Alex? You're the hardworking one, that's why I asked you. Okay, never mind. But basically, assuming this is what they have given you. Because here is a third order, and then this one is correct, 1, 2, 3, but it cannot be. Or else, I mean, if this is a 6, 4, 2, I will take this to be the answer. This will be the frequency. You get what I mean? So, and that's what I mentioned to you guys. The hint is very important. The hint is very important in the sense that when you work it out, you definitely need to make use of the hint. So in this case here, when you try to work out, so find the frequency at which the magnitude of the system is equal to 1, you already have the magnitude equation. Magnitude equal to 1. When you expand it, you got a 6th order polynomial. And they will definitely give you this. So in the event that if you cannot find something that looks halfway decent compared to theirs, something is wrong on your part. Okay, unless there's an error. Okay, in this case here, I suspected that this is an error. Okay, I suspect that this is an error because this will be a third order. It doesn't actually match any of that. But if this is the correct one, so that's why we need to work it out. I'll let you know. We need to work it out. So when you work it out, you will see that it will match it accurately and your answer is there. Okay, so once you work out the answer, you know what is the frequency. And what happened here is you can actually work backward to try to find out at this frequency what is the phase. right? You need to know the phase angle. From the phase angle, you take the phase angle minus 180 degrees. That means you plus 180 degrees, you will get your phase margin. Right? Because here they ask you to show that the phase margin of this system is 49.05 degrees. Okay, so you need to do that. Determine the maximum delay that could exist in the system before it would become unstable in the closed loop. So two things you need, because if you remember, right, if we assume that the phase margin is 49.05 degrees. Okay, so if we can assume that phase margin is equal to 49.05 degrees, how do we actually work it out? So your phase margin is basically 49.05 degrees. We need to convert it to radian. So this is actually equal to 49.05 divided by 180 times the pi radian. Okay, so in the way we know that last time when we work out the first part of it, we have my omega t. Okay, you remember, right? Because you have e to the power of minus j omega t. So delay in your Laplace transform. Wait, where are you leaving already? Where are you going?
Going home.
He just abandoned us like that. Oh, then we have to work and then he go and enjoy himself. Okay, never mind. It's okay. So, if you have any reason that you need to go off, it's okay because, as I mentioned, I need you all to work out all this. At least you try it out, so that the next session that we have, maybe before your exam, because your paper is actually mid-May, right? May is a Monday, 16th. May 16th. So when is your first paper? So early, 29. Control is the last paper. Wow, why every year like that? 29, so 25th. So what we can do is we can try to schedule one session, maybe about 18, 19. No, I mean we just take a time here. So you have any question you want to clarify, use that session, we try to clear. Okay, so I might do it together with Dr. Alfred Tan, right? I mean we will do together dynamics and control. We will spend maybe about 2-3 hours here. Both of us, if you have any questions, you just ask. We'll not be going through any of this, but we'll be basically Q&A. So that is why your Easter break is for you to quickly work out all this. At least at least you try to do it. You try to attempt the exam problem. Okay? Alright, coming back, we need to set this in order for us to determine, right? The question answers, determine the maximum delay. So this basically, we try to translate the phase into your phase margin. Because in the way we work it out, the phase margin is 49.05 degrees converted to radian. And then if we were to equate it, this will give us your Tmax, because phase margin is the maximum phase lag you can actually introduce to the system before the system becomes unstable. Okay, so you have 49.05 divided by 180 times your pi. And the earlier portion, you would have worked out what is the frequency. So this is actually known value. Alright, omega is a known value. This is your phase margin, and from here you can actually translate it into the maximum delay that you can actually have before the closed loop system becomes unstable. Agree? Agree? Because we work out phase margin provides you with the maximum phase lag you can introduce into the system before the closed loop becomes unstable. So now I take the maximum phase lag to equip it with what we can actually work out from the delay, which is basically your omega t. So your omega t max basically represents the maximum delay you can have for that particular system. Alright? Because that is the phase. When we work out what is the phase? The phase is omega t. Alright? Delay, when you can translate, is basically your phase lag. And we know that maximum phase lag is 49.05. So we can actually work backward to link back to your maximum delay that you can actually work out for the system. Okay? Alright? Any question? Okay, let's take a look. No question. We take a look at the next one. Okay, so this one again, as I mentioned to you, right? State the Laplace final value theorem. Okay, I told you right on Monday. You need to basically not to memorize, but you need to basically do a little bit of revision. Try to remember how the final value. So your Laplace. What is state the Laplace final value? So basically, this is what limit of t approaches 0 for your ft. Okay, it's going to be equal to limit of complex frequency variable approaching 0 for your s multiplied by fs. Alright? Agree? So this is your Laplace final value. Agree? That's your Laplace? Yes. Infinity.
Selamat. I want fractions.
Thank you. Or at least he's paying attention. Okay, so you see, this is how many marks? 2 marks, right? So you know, if you want your A1, every mark count. Okay, every mark counts. So you collect as much as possible. Don't give it up. Collect as much as possible, and yeah. So I told you, right, last year someone scored 100 marks in the final. So this year we hope we can see the repeat. Yeah. Seriously, I'm not joking. There was one guy who scored 100. I mean, all the 5 questions all correct. This is a paper that is actually doable. Okay, it's a paper that is actually doable. Okay, it's a doable paper that you can actually score 100 marks. Okay, so you can see that, right? I told you this come out again. State the Rupert stability criterion for a third order system. So just now we have actually worked it out, right? Just now we have actually worked it out earlier on. Your Rupert stability. So if you're given a third order characteristic equation, A3s cubed plus A2s squared plus A1s plus A0 is equal to 0. So I mean, once you have done it once, this becomes quite straightforward. All you need is your AI has to be greater than 0. And then you have another condition is A1 times A2 greater than A3 times A0. That's it. 2 marks. Okay. The only thing, disclaimer, all this not necessary will come out. You have to prepare. Okay. Not necessary will come out, but it's good to prepare, to get yourself prepared. Okay. So I mentioned these are the clear-cut one. They will also have root locus, they will have polar locus, stability and all that. So those things, so it's a change of mindset. Okay, so you are the first batch. So first batch student always get a little bit of discount. That's why first batch student, when you try to change your mindset, they make it a little bit easier for you. Okay, next year guys, sorry, come up. So it's the same thing like your aircraft performance, right? The first time when student uses stat, the question very direct. If you look at the main paper, you look at the receipt paper, very direct. Second year time, run around, he has more time to think, so you make it a little bit more tricky for your guys. Unfortunately, next year will be a new one. So next year batch will be good luck. Because I don't even know the receipt paper how it's going to look like. Because he left Glasgow already. Okay. Okay, so you can see this is explain what is meant by the dominant poles of the system. Okay, as we mentioned before, dominant poles of the system primarily is are those okay, dominant poles of the system. So I guess if you want to explain this, though it's 2 marks, so basically you draw the group, you draw the complex S plane and then you indicate the poles. So you can actually explain that the poles that are actually closest to the j omega axis can be on the left, can be on the right half plane. Right? If you have a system with many poles at 0, the pair of poles that are closest typically complex conjugate, closest to the j omega axis. So in a way, we can actually put it this way. Your dominant pole will be something like this. For a stable system, you will see something like that. Okay? You can have things like this. So in a way, the dominant poles will be this pair of complex conjugate poles. Okay, because why? Because from this S plane, complex S plane, you can actually see that this pair of poles are the closest to the j omega axis. So these are basically for a stable system because they can actually give you an unstable system. Your system is also very close to your j omega axis. Because why? Because your 16, your F16 is like this. F16 is slightly, the Fugoi is actually slightly to the right hand side of your complex conjugate pole. So what happened is they designed the feedback controller to try to attract the poles to come back to the diaphragm plane. So that is a stabilization, right, for your F16. So typically, you have a pair of your Fugoi is actually very close to the j omega axis, unstable. Typically, what happens is if you have fighter will have your Fugoi slightly unstable. Okay, so sometimes it can be a case like this. So when you have a little bit of a higher damping, you can actually have a pair of real roots very close to the j omega axis, but they are actually unstable. That is when you design for your fighter. Okay, your flight controller and all that, the design, you can see that kind of characteristic. Unlike your short period is always up, right? Short period has high frequency, very highly damped, so not too much of a worry for most of the time. Okay, all right. So that is your dominant poles that if you were asked to basically to describe. And of course, what happened here is among your complex conjugate poles, your dominant poles will have the smallest real part of the real roots. Your complex conjugate poles will have the smallest magnitude in terms of your real parts of your complex conjugate roots. Because the rest of them are all larger, right? This, they are all bigger in terms of magnitude. In terms of magnitude, they are all larger than your dominant complex conjugate poles. Okay? Alright? Okay, let's take a look of any question. Any question before we move on? We don't have much time, we have only about 20 minutes to go. Okay, never mind. Think about it, you still have April that we can come back and discuss. Okay, let's take a look of part B. Part B, what happened here is you have a negative feedback control system here. You have a unity negative feedback control system has a forward path transfer function given by this transfer function k divided by s plus 4 squared. So it's a third order forward path transfer function. Ask you to write down characteristic equation for this system and determine the range of k for which the closed loop system is stable. So standard, right? You work it out, closed loop. So first, obtain the closed loop transfer function. As what I mentioned to your guys, if this is already given to you, what is your closed loop transfer function? Okay? For the benefit of those guys who were not here on Monday, Okay, I mentioned to you guys your closed loop transfer function. If you are given your forward loop transfer function is gs is equal to k divided by s plus 4 squared. So what is your closed loop transfer function? Is gs divided by 1 plus gs. Please don't do what you did in your assignment or try to use the signal draw and all this and that. Okay, so as I mentioned, it's nothing wrong. If you have a lot of time, you have nothing to do, it's okay, by all means. But when you are running short of time, if you can just apply this formula and work out your closed loop transfer function. Why do you want to use I mentioned, like, so this is your GS, and then this is your CS, and then, so what I found is, so this is your RS, and then this is your ES, and then you say, okay, ES is equal to this, and then this is equal to your BS, and then BS is equal to CS, and then you link everything, and then eventually you work out closed loop transfer function of CS divided by RS. Okay, and then you move here, move there. You are trying to introduce error, right? This is clear cut, just do it. Okay, I mean, if you can do it directly, just do it. Because it's only 4 months, it's not worth around, it's not worth your time to think around with trying to work it out, based on the signal flow and so on. Unless it's a very complex problem, then yeah. Okay, so they are asked to find the steady state error for a step input of magnitude 5. Okay, so when you work out the closed loop transfer function, that is why you can see that the final value theorem actually comes in. Okay, so you need to basically work out. So in a way, so what happened here is you need to try to find out. They ask you to find out the steady state error for unit step input. So you need to work out, because now RS is equal to 1 over S. So you need to find out what is CS. And you need to, from here, you work out what is the CSS. When your input is 5, okay? Sorry, input is actually 5, because input of magnitude 5. So you need to work out what is your CSS. CSS is going to be equal to the limit of S going to 0 as multiplied by CS. Okay? So from here, you can actually work it out. The other way, as I mentioned to your guys, you can actually work out the DC gain of your closed loop transfer function. Okay? Closed loop transfer function, primarily your CS over RS. So if you can work out your DC gain, if your DC gain is equal to 1, okay? So your DC gain equal to 1 for the closed loop transfer function. So what will be the steady state value? Your CSS, when your input RS is equal to 5 over S, your CSS is going to be equal to 5. So as a result, ESS is equal to 0. Okay, so it's up to you. Okay, if you want to do it this way, you can do it this way. If you want to use a final value theorem, you can also use a final value theorem. Okay? Alright? Because this one, I can specify it that you're correct, because that's what I taught you. Okay? Okay, the last part of it is quite interesting. They ask you for value of k is equal to 24. Solve the characteristic equation to determine position of your dominant closed loop pole. Okay, so in a way, they were also quite kind to you. They ask you to determine solve the characteristic equation to determine the position of the dominant closed loop poles. They told you that the non-dominant pole is actually at S is equal to minus 6. Okay, S is equal to minus 6. And from the position of the dominant poles, determine the damping factor and the frequency of oscillation of the response due to the dominant poles. Okay, so what happened here is you need to basically work out your characteristic equation when k is equal to 24. Okay, so you need to work out your characteristic equation. It's going to be equal to your third order characteristic equation. So it's going to be equal to A3S cubed plus A2S squared plus A1S plus A0 equal to 0. And this basically can be written as s plus 6 plus s squared plus, alpha s plus beta. These are all known value. If these are all known value, based on this information, you will be able to determine what is your alpha and beta. Once you determine your alpha and beta, you know where the dominant pole is going to be located. Alright? Straight away from here, you let s squared plus alpha s plus beta is equal to 0. You can find out the location, right? Minus alpha plus minus square root of alpha squared minus 4 beta divided by 2. So you know where your dominant pole is going to be located. And that's what they ask you, to find the dominant closed pole location. And from there, determine the damping factors and so on and so forth. And the frequency of oscillation of the response due to the dominant closed pole. So the moment you have this is equal to minus zeta omega n plus minus j omega n square root of 1 minus zeta squared. Okay, so in a way, you can also try to find out based on what you have also worked it out. So it depends on the dominant closed poles. Okay, so this is the dominant closed pole. You can also find out what is the angle, because this will give you your zeta. Alright? Agreed? Because if this is your dominant closed pole, you know the location of the dominant closed pole, you can find out the angle. This angle, cosine angle, is going to give you your damping ratio. Right? This angle is theta. So cosine theta is actually your damping ratio. So straight away, you work out what is the damping ratio. So you know the damping factor. Frequency of oscillation, from here, you can actually work it out. Right? Because from here, you work out your damping. From here, you work out this is a real part of your complex conjugate, zeta omega n. If you know zeta, you can work out what is the omega n. You solve the problem. Okay, alright? Okay. Any questions so far? Okay. We have to rush a bit because they're going to come in and do some setup at 3:45. Unfortunately, beyond my control. Okay, alright, take a look of your question number 6. So again, you see question number 6, you can see that state the calibration equation. So your angle criterion calibration equation, whatever related to your root locus and all that, please, right? When you do your revision, try to memorize it a little bit, right? State the calibration equation, magnitude condition. So you have seen how do we need to actually make use of your angle criterion. You also have seen how we need to make use of your magnitude condition. Okay, used in your root locus analysis. So in your root locus analysis, you can actually see that that will be required. Your magnitude, that is your calibration equation. We just now making use of what is your calibration equation? K is equal to pi of distance from the point to your open loop poles divided by pi of the distance to your open loop 0. Right? So that is basically your calibration equation. Again, is 2 marks. Okay? Alright. Any question with that? So this one is within your control. It's not within my control. I can force you to remember that. If you don't want to remember, there's no way I can force you to remember. So it is basically it's going to be coming from you yourself. Okay? Alright. Part B. Okay, so unfortunately, we didn't really go through. I hope maybe Dr. Alfred Tan has gone through with you. Linearize. Have you done linearization? Not even with the dynamic. Because you do realize that basically linearization occurs more in the dynamics. Because dynamics, you need to obtain the equation of motion. So when you work out your equation of motion, like your aircraft and so on and so forth, right, your aircraft dynamics and so on, your flight mechanics, right, your longitudinal motion, axis and so on, they are typically non-linear equations. So what you need to do is you need to basically linearize it. And linearization, basically, a very basic linearization is what we call, you use a small angle perturbation technique. Right? Your small angle perturbation technique, like when you use sine theta approximated with theta, cosine theta approximated with 1, tangent theta approximated with theta, right, in your equation. And assuming that the perturbations of all this angle are very small. So that means you're saying that a perturbation of plus minus 5 to 10 degrees. So the deviation should not be that high. And in a way, what you do is you linearize it, you also linearize it about a particular optimal condition. Optimal condition, basically, if you have a rigid body equation for your aircraft, so you can actually linearize it at what we call straight and level flight. Your straight and level flight condition is primarily you have quite a fair bit of assumption, no pitching, no rolling, and then also your yaw angle also equal to 0. So you actually have all these conditions that you can actually set it in. And as a result, you use it to simplify your equation. Okay? You use it to simplify your equation. Unfortunately, you also restrict, when you design a controller, you also restrict the range of application of this controller. Because if, say for example, you have a pendulum, right? You have a pendulum, you have a swinging pendulum. So the easiest way to design a controller for this like inverted pendulum is basically fix a reference point. So typically what we do is we will look for equilibrium condition. So what is the equilibrium condition for your pendulum where the pendulum is actually in the vertical direction, right? So if you use that to use it as an optimal condition, you can actually have a solution related to when theta is equal to 0. So you work out the velocity associated with that, acceleration and so on, as a condition that you want to use, and you linearize it. And as a result, you have a linear model, because if you remember, what is the linear model of your pendulum? Your linear model of your pendulum is going to be equal to what? Your linear model is going to be theta double dot plus g over L theta is equal to 0, right? This is a pendulum. Okay, remember that? Theta double dot plus g over L theta is equal to 0. Okay? In your non-linear state, you have theta double dot plus g over L sine theta is equal to 0. Okay? G is your gravitational constant. This is the length of your pendulum. So in this case here, this is a non-linear equation. This is a linearized equation. Okay, so you can actually see that. But in this equation here, if you were to design a feedback controller based on this, your feedback controller will only be good because why? This is actually perturbation about theta is equal to 0, and you're also looking at theta, delta theta to be equal to plus minus maybe 5 degrees, very small angle. So your feedback controller will work when theta is about equilibrium condition. Theta is actually about the 0 and oscillating at a very small angle. So if you want to oscillate at a very large angle, your controller might not work. Okay, so likewise, if you look at your inverted pendulum, it's the same thing. If you have a pendulum, you invert it. If you linearize it about vertical angle, right, vertical direction, so you can actually try to control it. Okay, you can actually try to control it. That means, if you remember, if you use a cart and a pendulum, you can actually move the cart forward and backward on the track to try to balance this pendulum. Okay, so you can actually design a feedback control law to make sure that the pendulum always stays vertical upward. But if you try to balance it at 45 degrees, it will be very difficult. But you can actually design a feedback control law. What I'm saying is, if your angle is very small, you can actually balance it. If your angle becomes very large, apply the same control law, might not be able to work. Because why? Because your model is actually linearized about the vertical upright condition. So if your deviation is actually outside, it might not work. So that is the difference between a linear and a non-linear model. In a linearized model, when you design a controller, on paper, everything should work. But in reality, it might not. Okay, in reality, it might not work. Okay, so coming back to this problem here, they ask you to plot the root locus for this system. Okay, so they say, okay, plot the root locus. So in this case here, you have 1, 2, 3, 4, 4 poles, 2, 0. 4 pole, 2, 0. What is the relative order? 2. Asymptote, angle of asymptote plus minus 90 degrees. Okay, so plot the root locus for this system. You may estimate angles of departure from or arrival at any complex singularity, but you must calculate the position of any double points and points of instability. So in this case here, do you think you're going to see any point of instability? Will we see any points of instability? Because in this case here, it's very clear cut. Okay, in this case here, you have a pole at 0, you have a pole at -1, you have a 0 at -3, you have a pole at -4, and then you have a 0 at -5, and you also have another pole at -6. Right, 1, 2, 3, 4. So in this case here, if you work it out based on either what Murray has given you or what I've actually taught you, this will be part of your root locus, this will be part of your root locus, this will be part of your root locus. So remember, if you need to indicate your root locus, you need to indicate the direction. Right? As we mentioned, based on Mother Nature, the pole will always want to go to the 0. Don't do the reverse. It's not going to be 0 going to the pole. If you get 0 going to the pole, then that's it. You will lose all the marks. So it's always a pole going to the 0. So you have pole at -6 going to 0 at -5, pole at -4 going to 0 at -3. And this two basically is going to form part of your root locus because you have two poles. So what happens is you have your double point. Okay, you have the double point, and you need to actually work it out what will be your asymptote. Angle of asymptote we mentioned is going to be plus minus 90 degrees, right? Your angle of asymptote is equal to plus minus 90 degrees. So you need to find out what is your centroid, right? Centroid of your asymptote. Your x is going to be equal to, in this case here, 0 plus -1 plus -4 plus -6 minus -3 minus -5 and divided by 4 minus 2. So in this case here, you got -3. This is +5 plus 5 plus 3 is +8. +8, this is -11. So it's actually -3 divided by 2. So it's equal to -1.5. So it's somewhere around here. Okay, so that is your asymptote. So in a way, you need to calculate this, your double point. So your double point, how do you calculate the double point? The double point is going to be dg ds. And that is why in your dg ds, you can see that they have already given you the hint. You may find it useful to know that the equation 2 of s raised to the power of 5 plus 35 s to the power of 4 plus 236 s equal to 0 has all the solution. So in the way, when you try to work out your dg ds, if your polynomial, when you work it out, dg ds, set it equal to 0, it's not going to be equal to this. Something is wrong, right? It's on your part, something is going to be wrong. So try to do something to make sure that somehow it works out to be the same. But you don't just take this and say that, hey, that's mine, huh? You have to work it out because we will check also, just to make sure that you know what you're doing. But the hint is very obvious that you definitely need. So when they give it to you, they will not give you anything that is not required, they will not give you redundant things. So in a way, when they give you this, definitely you need to use it, and from there you can actually work out what is your double point. So in this case here, very obvious. Where will be the double point? The double point is going to be equal to minus 0.5195. Right? Because all this are all complex number, it cannot be the double point. So the double point has to be on the real axis. So when you have the double point on the real axis, you can actually try to work it out. This will be the double point, minus 0.5195. So this is where it's going to be breakout. So 0.5195, and it will go this way. Okay, so it will go this way. So K increasing, it will move in that direction. Okay, all right. Okay. In this 2 and 3, from your plot, estimate the value of K that will give the dominant complex pole damping factor of 1 over root 2. So what is the angle of 1 over root 2? 1 over root 2 is root 2 divided by 2, 45 degrees. So again, you need your protractor. Measure 45 degrees, intersect. From there, you find out what is a complex pole. From there, what condition are you using? Calibration equation. You need to make use of your calibration equation to find out your K value. Okay? You need to find out your K value based on your calibration equation. Explain what would happen to the system response as gain K tends to infinity. So what will happen? Because I've shown you roughly this is increasing of your gain K value. So this is your root locus, increasing gain K, what will happen? So what do you think when gain K becomes very large? What will happen to the response? What will happen to the response? The response will be very oscillatory. Alright? Because when K becomes very large, you are moving vertically upward. As a result, your damping becomes smaller and smaller and smaller. When your damping factor, your damping ratio becomes smaller and smaller, response becomes more and more oscillatory. Because why? This will be your dominant closed loop poles. Right? Because this pair of poles in your closed loop closest to your J omega axis. Agree? Because the moment it's closed loop, you can actually ignore all this. All these are all open loop pole location. Okay, they are all open loop pole location. The moment it's closed loop, you look at what is on the root locus. So when K becomes very large, becomes infinity, so what happens here is your damping factors or your damping ratio becomes very small. So as a result, response becomes very oscillatory, overshoot becomes larger and larger. Okay? Alright? Any question? Any question? No question. Okay, no question. Then today we will end here. I think you have some activities, right? After this 4 o'clock. So don't go away, don't go home, please. You have any football games or anything, please hold it. Okay, alright. So what I'll do is I will try to find a time. I will arrange with your class rep. So maybe you let your class rep know what will be a good time for your guys that you want to basically have maybe the last consultation before your exam. Okay?